Guys, you can hear me?
Yes, sir.
Okay, good.
Yes, we can.
Yeah. So let me quickly start it. Share screen. Okay. So again, sorry that we are starting this thing late, and I am late anyway. I tried as hard as possible to come back on time. It's not always possible. So today is 17th March 2021. Right. So what I'm going to start today and briefly do today, basically start with an introduction, is we derived Maxwell's equation last time. And initially I thought I will do a little more on Maxwell's equation, but I think I will come back to it after a couple of classes over here. Talk about things which are conserved quantities and stuff, but I'll do that after this, after these two classes. So what I'm going to do is I'm going to talk about action principle. Okay. So all of you have done action principle in your classical mechanics. So what I'm going to do is I'm going to talk about electromagnetic action. So from today, I'll start on,
Sir,
yes.
sir, before starting, I have a doubt regarding the last lecture. Yes. In the last lecture, you have derived the Maxwell's equation like divergence of B equals to zero, which we know that is a consequence of magnetic absence of magnetic monopole. Uh, but in order to derive that, you have written that V is uniform or V doesn't have any space dependence. So how does it relates with the magnetic absence of magnetic monopole? I mean to say that if V is space-time dependent, will divergence of B is not zero?
It will still be zero. So that was one of your problems probably, or I mentioned that we try to do it, that make V as a function of R and T and still see that these things follow. It will just be more messier calculations. You don't have to do with this simplified treatment of V being uniform. You can have a V as a function of R and T and you'll still go land up with the same equations. So that was, I think, did I give you as a homework that problem? I don't know whether I gave you as a homework, but anyway, so yeah, I think last time I gave it as a homework, but yeah, so you can go through this whole process by doing this V not equal to constant, but have a V as a function of R and T. And then, so maybe I'll actually give it as a homework. So let's see. So, um, in the homework problem, I'll put as a homework. So then also you'll see that this thing works out. It's just going to be more messier. So you can try it out. Try it out.
Okay.
Yeah, so it doesn't depend on the V is equal to constant. That's what I'm trying to say.
Okay.
Right. So I'm going to start on action for electromagnetism, and then I'll go into equations of motion for particles and fields. So as I said, you guys have already done action in classical mechanics. I think all of you have done. So I'm not going to dwell a lot of time on the general principles of how to get equation of motion from actions. But today I'm going to do a brief review of that because um, maybe there will be certain things which you have not seen before. Maybe you have seen it before, some of you, to see whether and these things will come in handy when we actually write down the action for electromagnetic fields. Okay. So to start with a recap is so so your action, as you know, this is the time integral, is the time integral of the Lagrangian. So I can write down the action like this. So let me write down the action. Okay. So I'll call this action S, which is what you generally call. So going from some state 1 to some state 2, that gives from T1 to T2 LDT. Okay. So this is initial time or initial configuration, initial time, and this is final. Okay. So that is by definition the action. And if I basically take this action and do an infinitesimal variation of that action and then equate it to 0, we get the equations of motion. That's the idea. Now, to look at it, to say it a little more clearly, what is important to know is that if I have an infinitesimal variation of the path, so this particle, I'll give you an example of a single particle, and it will be evident why I use a single particle, because a lot of things become very evident in the simplest example. I take the particle from an initial state to a final state, it goes through a path. So if I have an infinitesimal, a very small variation of that path, then what I want to say is that this action, this S12, it remains stationary. So it does not have an infinitesimal change, although I'm changing the path of the hand. And if, and it's very important, if it is the correct path. So this thing is stationary only if it is the correct path. Also, provided that the initial and the final configurations are held fixed. So let me write down what I wanted to say is that, so if I make a infinitesimal change of the path, okay, the action, okay, is stationary. And what do I mean stationary? That is, it doesn't have, although the path has an infinitesimal change, the action doesn't have an infinitesimal change. So it does not have infinitesimal change, but that depends on what? It depends on only if it is the correct path, plus provided the initial and final configs are fixed. Okay. So we have to carefully remember this thing, that this gives the equation of motion the correct path only if the final and initial configurations are fixed, and only if it is the correct path, then only the action does not change when I make an infinitesimal change to the path. That is what you have learned in your classical mechanics, or I think mainly in classical mechanics. Now the only change in this action, so the only change in this action S, okay, I cannot see when I write, yeah. The only change in this action S comes if I change basically the initial and the final times, including alteration of those times. So if I change, or rather say if I change small, infinitesimal, again, infinitesimal, okay, at the initial and final times. So if the configuration at the initial and final times, if I change those configurations very, very little, including changing those times a little. So if the times are changed also a little bit, then the configuration will be changed. Then only those, including time, including changing T1 and T2. So either the configurations or time. Then the only change in the action, there will be a change in the action. So they'll have one small change in the action. And that I will write as G1 minus G2, where this G will be a function which will depend only on the dynamical variables at that time. So this G is then a function, and this function depends only on the configuration or variables at those times. Okay. So this is what uh, the action principle states. Now, what I'm going to do today is I'll quickly go through an example of a very, very simple recap of this action principle from 3 different viewpoints. So you are very well aware of the first viewpoint, but perhaps most of you are aware of the second viewpoint, but you may not be aware of the third viewpoint. So let's start with the first viewpoint. Okay. So let us start with the first viewpoint, which I will call my Lagrangian viewpoint. Okay. This is the most common that you have always used in classical mechanics. Okay. So I will take a very simple example where non-relativistic motion of a particle of mass m moving in a potential v. So example will be non-relativistic motion of particle of mass m moving in a potential which is V, R, and T. Okay. So that's a simple example. It's as simple as it possible. Okay. Of course, you could have a not in a potential, just a kinetic energy, no potential. That will be even simpler. So in this case, I can write down the Lagrangian. So let me write down the Lagrangian. The Lagrangian is half m, then dr dt whole squared minus v r t. Okay. Now, one thing I want to state over here, the independent independent variables over here are R and T. So what are the independent variables? The independent variables are R and T. Okay, and is non-relativistic. As you can see, I have just some simple basically kinetic energy minus potential energy. I have used the simple kinetic energy term, non-relativistic formula for it. Now I'm not going to do the variation. So there are two variables. So what you have to do is you have to change these variables. Okay, so there are two variations. Okay, the two variations. In one, I'll change my R, a small variation in R. So that goes to RT plus delta RT. And the second variation is actually the change in the time variable. So T goes to T plus delta T. Okay. Also, I will have a choice, okay, of the endpoint variations. Okay. So I'll think of the choice of the endpoint variation. So if I write down the endpoint variation, so delta T at T1, let me call it as delta T1, and my delta T at T2, let me call it as delta T2. Remember, the endpoint variations will give a change in the action, whereas the other variations will not give a change in the action. Okay. So now you vary the action, and when you vary the action, you'll get your equations of motion. So you vary the action, and this is actually a homework, although a very easy homework because we've done it many times, but you have to do it exactly in the way I'm giving it. Okay, so you vary the action. It's a trivial homework, but you still have to do it. So one variation is the variation of delta R, right? The other variation is the variation of delta T. So when I vary the delta R, okay, the corresponding equation of motion that I get, the corresponding part that I get is I end up with this equation, which is okay. This is the one that do. So please do it. I mean, this is your homework, so please do it. Okay, and you can vary the delta T. Vary the delta T, then what you will get is ddt of m plus v is equal to del T of. Okay, so these are the two equations that you will get when you vary these two independent variables and put the total variation to be 0. Okay. Now, as I said, the variation of the endpoints will also give you a, as I said over here, the variation of the endpoints will also give a change in the action, delta S, and that defines this G, okay? The things that comes from the variation of the endpoints, which is depending on the variables at the endpoints. So I can calculate my G over here, and this will turn out to be m dr dt dot delta r. So there will be a r term, and then plus, no, there will be a minus, I think, minus of m, yeah, plus p delta t. Okay, so this is what we, so this is basically This is basically P dot delta R minus E dot delta T. Okay, this is what I will. So this term will come. Okay, this will depend on the total time derivative given at the change in input point. So this comes from the, this will come out of the total time derivative. Okay, at the endpoints. So now if you look at these three equations, if you look at this first equation, that is just the Newton's laws of motion, right? So this equation is just Newton's law of motion. Okay. The second equation that came from this delta T, this equation, this is the conservation of, so if I put my static V to be static, so it doesn't depend on T, then this del T of V, that will become 0, right? So then the left-hand side, this ddt of half m dr dt whole squared plus V, that is equal to 0. So this basically tells you the conservation of energy for a static potential. So this is conservation of energy for static potential. Okay. And the third one, what is G? We'll come to this perhaps in the next class or maybe the next to next class. So this will again be related to conservations and invariances and stuff like that. So this, I guess, is clear because you must have done this many times in your classical mechanics. Okay. So to make practice, what you want to do is that this is a homework.
Sir, hello.
Yes.
So can you explain what do you mean by the variation of time? Like if we change RT to RT plus delta R, it means that we are varying the path, right?
Yeah, there are over here in the Lagrangian, there are two independent variables, right? So one is R and one is T.
R is a function of time, so that is the path.
R is a function of time, but time is also an independent variable over here. Doesn't what is the independent variables in a Lagrangian? R and T, right? Q, you say Q in classical mechanics typically. So you write down your delta S in terms of your dt. I don't. So that was a homework. I don't want to tell you exactly.
We
So
only
write
vary
down
the end points T1 and T2, or
so the endpoints are the total time derivatives. Okay, that will be at the endpoint. Have you done variations before? I mean,
yes, that we have I've done. This we used to vary this path. Just the first R
yes,
changes
the
to
path.
R plus delta R.
Yeah, R plus delta R, but there is a, when you write down this whole variation, changing R and T both, because there is a T, it's going from T1 to T2, so you can change your T also, right? When you do that, there will be a term which will be proportional to delta R, there will be a term which will be proportional to delta T, and there will be a term which will be a ddt term. Please do the variation. Please write it down fully as a homework problem. If you cannot do, then we'll of course do all these homework problems. So let me, although showing this means showing it completely. So I think it has already gone. Is it there? Just a minute. Okay. So if I want to do my variation, so this is a homework, but I'll give you some hint. Basically, it's doing a homework. So homework is derive the variational results of delta R, delta T, and G. Okay, this is your homework. Okay, but if you want to do it a little more, you have your delta S, right? So I'm not going to do it fully because then it is a homework. This, as you know, was a function from 1 to 2, okay, dt. And then there was an L, which we wrote before, and you have to vary that L with respect to these variables. So what you will have there will be dt, and what you will have is something, 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 okay, delta R, okay. Then you will have something, 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 delta T, and there will be two something, something, something times delta T, okay. One of which will turn out to be a total derivative, okay. And that will give you this G, the other will give you your two other variations. So I just ask you to write it down in detail and do it. How many of you don't know how to do it? So let me ask actually this question. How many are you having difficulty in doing this thing? Hello? Hello?
So I've never varied time before. We kept the fixed endpoints and we varied only the path. So I understand what Saurav was trying to say.
Okay. Okay, let me sort of then try to. Why don't you try today? On Friday we will. If you cannot do anything in Friday, then we will do the first one. I'll do the first homework on Friday. The second homework you can do by yourself. Okay.
Yeah. Okay.
Yeah. So one of the things you see the reason you have not varied time is that you wanted to do equation of motion, right? And see, when you do delta R, you get your Newton's equation of motion, right? The variation of delta T doesn't give you an equation of motion. What it does is a conservation law, right?
Yes,
If you look at what I've written, the delta T gives you an energy law. That is, energy is conserved for a static potential. It is not an equation of motion, but it's important physical understanding of this system, right? Which you know already, that the
What
potential
does
is
it
that.
mean physically to vary time? Like when we say that we are varying the path, we say that the endpoints are fixed, and so we are varying it around the classical path, and around that this variation in axis would be 0. But when we say that the variation is in time, what does it mean physically?
That means the endpoints are also moving. That means your endpoints are also moving, and that will give you two kinds of variation. One will be a total derivative and one will not be a total derivative. If you write down your Lagrangian in the way that I've written over here, I can't see both the things actually. So the write down the Lagrangian and you just vary it. Take R and T because V has an R and T, right? Your potential is a function of R and T. So you can vary it both with R and with T. So think of this as a function. Forget about calling it a Lagrangian. Think of it as a function L, some function F, and you vary it in two parameters, R and T. And then you want to say that the variation has to be 0, okay? And that would mean that putting certain things equal to 0 in your total variation. And that's what you do. When you put that certain things in the bracket corresponding to one of the parameter variation to be 0, you get certain equations. the variation of the R gave you the equation, which was this first one, this delta R. The variation of the T will give you another equation, which you know, I mean, you know, the variation of time variation gives you your energy conservation, that you know. So you should already think that what you're getting is not completely bizarre. It is that your delta T variation is giving you an energy conservation. But there is also a total derivative at the last point variation is coming, which is basically what I said before initially, that there will be a contribution to this delta S, which will depend on this total derivative, which will not, I mean, which by hand you have to put to 0. And that gives you something which is like this, P dot delta minus C delta T. And if I want to put that equal to 0, saying that this total derivative is also equal to 0, that gives you another conservation law. And this kind of conservation laws, you know, you have talked about why you call G, because these G's are called the generators of conservation laws. So this total time derivative is generating a new conservation law. I didn't want to go into in detail, but if you cannot do this, then I will do it next day, okay? So that basically means please try it today to calculate this.
Okay.
So try it today. If you can't do it, I will do it next day. On Friday, we'll do it. Okay. So one thing, please tell, whenever you are the share screen is missing, you must immediately let me know, because I'm looking at a computer, I'm looking at my iPad, I cannot see both the things, so I don't realize when the share screen is going away and stuff. Okay, so let us look at another viewpoint. Okay, so we had what I call viewpoint A, which was the Lagrangian viewpoint. I can have another viewpoint, which I will call the Hamiltonian viewpoint. Okay. Okay. Now, your action, of course, is LDT. So in the action, you have to have an LDT, but I can write down my L in terms of an Hamiltonian. So in my Hamiltonian viewpoint, the Lagrangian that I write, this is like this. So I can write down, so we look at the initial Lagrangian that I had written over here. Where is it? Look at this Lagrangian, okay? I can write this Lagrangian in a form which is like a Hamiltonian. So what I can do, I can write it like this. Excuse me. Okay. Where my H is equal to E squared by 2m plus. So now if you look at this formula, you realize that the independent variables now are not two. Previously, the independent variables was R and T, but in this Hamiltonian viewpoint, because I have rewritten it, I have one more independent variable. So now I have three independent variables. So I have three independent variables, okay? R, T, and my P, okay, the momentum. So momentum is an equivalent independent variable over here. So now I can take this LGT and I can do a delta L, okay? So do a delta S. To do delta S, I need to do a delta L, but now there'll be three variables. The function is a function of three variables. And I do the same. Yes.
In the Lagrangian viewpoint, we also have R dot as an independent variable.
That's right. Over here, we don't have an R dot in my simple formula, right? So you could have an R dot that would have given you certain more, you know, dissipation term. Over here, we don't have it in this simple equation of a non-elastic motion in a particle.
The first term is a R dot term.
Sir, in the kinetic energy part, there is a R dot.
See, the kinetic energy part, there is an r dot, but the way I want to write it as two terms, r and t. So over here, I'm taking my r and t as the two independent variables. Okay. If you try to do an r dot, if you just write it as m r dot minus vrt, then you will come up with another equation, and that equation will give you something which will come later. So I don't want to spoil the surprise. You will have another equation which will not be either of these kind of equations. It will give a different kind of equation. It will not be an equation of motion. It will also not be a conservation equation. It will be a different kind of equation. I will come to that in a moment, in 5 more minutes. Okay. The reason I'm choosing these variables has certain, reason has certain reason to it, certain meaning to it. So it will quickly become clear why I'm choosing variables the way I'm choosing it, and I could in principle choose other variables that will not give you equations of motion. Okay, that's the whole point. So I've chose variables which will give me something which is fine in the system, which will give you some equation of motion, but I could have chosen an r dot, and I will choose an r dot later. Just give me a moment, okay? I'll come to that. So yeah, see, I'll come to that in 5 minutes. It's a good question that actually tells you what happens later. So where is it? Yeah.
Sir?
Yes.
So
Nikhil?
in this case, why are we not taking R2 to be an independent variable?
Huh? Sorry, can I see again, Nikhil?
In this case, why are we not taking R2 to be an independent variable?
Why I'm not taking, as I said, I will come to that in a moment. Just give me 5 more minutes where I will take r dot to be an independent variable. And as I said, it will give you something different. That's actually a key point of this lecture, what different it gives. So just give me 5 more minutes. Let me finish this Hamiltonian viewpoint, then I will come to that, okay? So over here, these 3 variables in the Hamiltonian viewpoint, I can again do the variations. And if I do my delta R, now over here, what I will get is this will lead to my dr dt, and this will be del H del P, which is equal to P by M. This is for delta P, sorry, it's for delta P. Then I will do for delta R, okay. Then this will be the opposite, my dp dt, okay. This will be minus del H del R. This will be minus grad V. And if I do my delta T, it will be dH dt is equal to del H del T. And similarly, this endpoint variation, which is the total derivative thing, this endpoint variation will give me the G, which is basically again same as before, P dot delta R minus H delta T. Okay. So couple of things that you should immediately see is that the endpoint variation in the Hamiltonian viewpoint is basically the same as in the Lagrangian viewpoint, where in the Lagrange, if you sort of associate that the Hamiltonian is the energy, so this H and E is the same, then this endpoint variation are the same, okay. And the other things are basically that you have this equations of motion that is coming out, okay. So instead of the second derivative equations of motion, we have first derivatives. So these are first order equations, and exactly the same that I had before. So these equations are exactly equivalent of the previous equations. In fact, what you can do, that you can try to show that I can get the same equations of motion starting from this and then writing the Lagrangian in the Hamiltonian viewpoint. You can basically go back from these equations of motion. You can go back to this previous equations of motion. that you can show. Okay. So again, that will be another homework. So just again, this is another homework which is there, which is again derive the above equations. Okay. This is another homework. Now, the reason I wanted to do this two different viewpoints and giving the same answers, so saying that I can write down my Lagrangian in a different way in terms of the Hamiltonian, I can now come to the third viewpoint. Okay. I can now come to a third viewpoint, which is some way a mixed Lagrangian, a mixed viewpoint. Okay. So what I'm going to do over here is I'm going to a third viewpoint where I'm going to choose my action with different independent variables. So all of you are talking about R dot, right? So let me take R dot also. So now let me go to a mixed viewpoint. So a third viewpoint or a mixed. Okay. So in this third viewpoint, let us have variables which are mixtures of previous variables in a sense. So let us choose variables R, which was there in both Lagrangian and Hamiltonian. Okay. Then let us take P and let us take velocity V. Okay. Now V is R dot, right? So I've taken a viewpoint. When I'm going to choose, I'm going to write my Lagrangian in such a way that these variables will be there, and then I'm going to minimize my action with respect to these variables, and we'll see what happens. So I can write down this Lagrangian like this in terms of these variables. So I can start with my previous, this P dot dr dt, that kind of stuff. And I can try to mix this Lagrangian, the Hamiltonian viewpoint Lagrangian, and the original Lagrangian to bring the third Lagrangian. So I'll write it like this. So P dot okay. So you'll see that this is exactly the same as the first one, the first Lagrangian, because I've essentially added a term which is 0, the first term. So I've written the second term as the Lagrangian, and then added the first term, which is basically 0. And in this thing, my H, which is a function of R, V, P, and T, okay, this will come out to be my P, okay, dot V, okay, plus half mv squared plus V RT. Just give me 1 second. I'm taking a class. I am taking a class. I'm by this. Okay, so okay, so this is what it is. Now I can again minimize these 4 things. So let me write down the equations what I will get. So first let me do this delta R. This will give me my dp dt is equal to minus del h del r is equal to v. This is what we got before. Then I will have delta p, which will again be like previous del r del t, which is equal to del h del p, okay, which is equal to v. So this is exactly what we had before again. P by m was v. So now because we have a v variable, so writing it in v. Then we'll do this delta t, which will give me my dh dt is equal to del h del t. Remember, this is exactly the same that we got in the Hamiltonian as well as in the Lagrangian case. So if my energy over there, the potential was a static potential, in which case your del h del t will be 0, then your energy is conserved. That was what we get. So this is the exactly same equivalent. Now delta v is different. So if you write down this full variation, then we'll see that delta v will give you something which is different. So you'll have minus del h del v equal to 0. Okay. Because this will come associated with your delta v. This term will come associated with your delta v. And that would give me p plus mv. So now you see this variable which I had is an interesting variable. Why is it interesting? Because if I have this variable, this number 1 does not give an equation of motion. Okay. It doesn't give an equation of motion. It doesn't give a conservation law as well. Okay. It doesn't say that the total energy is conserved if this is that. Okay. Because dv dt, okay, in this equation of motion, because dv dt is not there in the Lagrangian. This doesn't give an equation of motion because dv dt is not there in the Lagrangian. Okay. So what this r dot or this v thing gives is something very interesting. It actually gives us a constraint equation. So in this particle moving in this thing, there is a constraint which we always use, which we do not realize, is that my momentum is given by mv. So what it gives is this is a constraint equation, defines, okay. So if I had an r dot, it would have not given you an equation of motion or a conservation law. It would have actually given you a constraint equation. So depending on how you choose your variables, some of your equations that comes out of it are actually equations of motion. Some of the equations that come out of it are conservation laws, especially when it comes to the generator G, okay? And some equations are actually constraint equations. In fact, the reason I'm doing this is that when you will do your Lagrangian or your action for electromagnetic theory, you will actually see that Maxwell's equation that comes out of action, electromagnetic action, will basically consist of two parts. One which are basically equivalent of equation of motions, and one which are basically constraint equations. So this 4 Maxwell's equation, not all of them are what is equivalent to equation of motion. Some of them are actually constraint equations. And that comes from this simple example. Okay. Now, after this, what I wanted to do is I would talk about a little bit of invariance and conservation laws. Okay. But that I will do next day. Today as a short class, I just wanted to give this. And so this last part is very important. Most of the time you don't get to see this in your classical mechanics. I'm not sure how many of you have actually thought of this, but your variational principle actually can lead to different kinds of equations. Some of them are equations of motion because that's how classical mechanics you actually did. But some of them are basically constraint equations. And this is a simple example which shows that there is this constraint equation. Okay. Now, in our homework, what is important is that you do the first two variation for the Lagrangian and for the Hamiltonian. And if you cannot do it tonight, then on Friday, I will basically work out the Lagrangian case. Okay, this I will work out for you. Best is to go back to your Goldstein and just look it up, how to work it out. This is simple. I think this is already given in Goldstein. Maybe not the same variables, but it will be there. Okay. So next, what I'm going to do is I'm going to talk about, as I said, conservation laws, and then go into, so that's a long thing, that's why I'm not starting. I'm going to go into action for action and invariances and all this stuff. So in detail, okay. Okay, so now you can ask questions if you have.
Excuse me, sir.
Yes, say it loudly.
Hello.
Yes,
Sir, can you just go up a little bit?
up.
Sir, in the Hamiltonian viewpoint,
Hmm.
when you say dr by dt is p by m, it essentially says that p is mv, right? Why
Hmm.
is that an evolution equation and that a constraint equation?
Yeah, so no, I didn't say over here that is the evolution equation. I said the evolution equation is the next one, this one. So the first point, you see there was one evolution equation and one conservation equation in some sense. The next one, you have an evolution equation, a conservation equation of energy, and then dr dt again is a v, right? And so over here, this comes as the constraint equation. It's true. But in this case, it's comes obvious because you do not have a dvdt over here. In the third one, the reason we have, see if we adopt, see all of these are adopting the same thing in a different way, right? So if we adopt this definition of V as P by M, okay, then that this whole thing, okay, let me be very careful about it. If we adopt V as a definition, as P by M as a definition of V, then you will recover these Hamiltonian descriptions, okay? So you go over here, and if you adopt this definition, that your velocity, the definition of velocity is P by M, then you will go and you will recover your Hamiltonian description. Alternatively, what you have done is that you have start with the Lagrangian And then if you adopt the definition as V is dr dt and P is equal to mv, then you will go back to your Lagrangian viewpoint, the first one. So depending on how you adopt, whether you adopt the definition, typically when you have gone to this generalized coordinates, you have realized that generalized coordinates, your P being independent is not the same as m dr dt. We have m, we have r, and we have t. So from r and t you could get dr dt. Over there, r and t are independent, but when you went to the Hamiltonian thing, we had p as independent. So it's not the same as going from r to t, depending on how you look at the definition. So if you look at the definition of v as dr dt and p is equal to mv, then you will go to your Lagrangian definition from your final thing. If you make the definition of v as p by m, then we'll go to the Hamiltonian definition. These two look the same, but these are not fundamentally the same. So in one case, your definition of v is p by m. Okay. In another case, your definition of v is dr dt and p is equal to mv. So in generalized coordinates, remember when you were taught classical mechanics, you were taught that otherwise, what is the reason for going into Hamiltonian? Why do you have p as a independent variable? You could have got p from just from r dot, m into r dot, that you have got a p. But in the Lagrangian, r dot is an independent variable, but p is not. Over here, the p is an independent variable. So it depends on how you define your velocities. So you can go from one to the other. And what you have actually is, so what it seems is that you'll think that v is equal to dr dt is all that you need to go into your previous definitions. But I mean, that also will not give you exactly the same way the g's will come. So this variation of delta, delta t, all these things will become different. I'm not sure I'm very clear of what I'm telling you, but what I'm trying to say is that these two are not exactly the same thing. I mean,
Sir, actually, what I got from it was that, sorry, am I audible?
yes, you are audible.
So basically, let's say if you do not assume that V is dr by dt and you consider V and dr by dt as separate entities, then in the third viewpoint, you're adding information to the Lagrangian, right? And if you do not assume that, then these two things are exactly the same thing. So basically, what I got is that in the third mixed viewpoint, if you say that V is dr by dt, then your variation of momentum does not give you any more information, and the rest three is equivalent to the other two viewpoints.
Just
From
hold
what
on
we are
again.
getting.
Sorry, just hold on. Yeah, I'll just come. Hello. আমি জানি না, আমি ক্লাস নিচ্ছি, কি করতে হবে বলো। আচ্ছা, দাঁড়াও। Just hold on a minute, guys. Some people is coming from the security. Just give me a minute. Sorry about all this thing. Really, sorry about this. This happens when I take class from house, which is why I don't want to take class from house. Please say it again.
Sir, so basically what I wanted to ask is that in the so basically, let's say if you have three independent variables, right? So no matter how you look at it, you'll always have three independent variables. In the fourth viewpoint, you have added one more variable, and because of that, obviously there would be one of them would be dependent on the other three. And because of that, the variation of momentum, if you'll see, does not result into any meaningful equation. It simply says V is equal to dr by dt, right? And the rest three, from the rest three, we get the same thing as we get in the Hamiltonian viewpoint.
Absolutely.
So basically, it just sets up that the mixed viewpoint also is an equivalent viewpoint to Hamiltonian view.
Absolutely.
Right. That is the point of exercise. But I do not understand why do we need then to consider this mixed viewpoint if it does not give any more.
Because, yes, why is that? Because when you will go into your electromagnetic Lagrangian, you will see that this mixed viewpoint will come in handy. That's why. I mean,
Okay. All right.
why the whole reason I'm doing this is I'm preparing you for the things that will come. I mean, you are used to doing the Lagrangian viewpoint. Most of you are not used to doing even the Hamiltonian viewpoint in an action, although you can, which I just showed you that you can, and you'll get the same kind of equations of motion. And the idea is that you can write down anything. So in the Hamiltonian, you cannot add anything else, right? Because Hamiltonian is by definition has some form. I mean, Hamiltonian has these as the variables. Similarly, Lagrangian is these are the variables. You cannot add. So if you add something that will not become a Hamiltonian or a Lagrangian viewpoint, you will have something different. Now I can add some other variables also. If I can carefully write down some other variables, I can add it over here. But at the end of it, you have to write down the whole thing, the Lagrangian in terms of the variables, obviously. So quantify it the way I have done the mixed case. And that will give you equations which will not be the equations of motion as you have correctly pointed out. Now the reason I'm doing this mixed one is that when you go into your Lagrangian for your electromagnetic radiation, I mean your EM theory, electromagnetism, you will see that there will be this, so you will see that there are dependent and independent variables over there, and you have to choose what are dependent variables and which are independent variables. Remember, you have E, you have B, you have you have A, you have phi. There are other things also, so you don't know which one you need to choose exactly. And some of them will be independent, and some of them will come as this mixed variable case. It will become clear when I does this whole Lagrangian, and it will not be so trivial. It will see that it's quite complicated. You'll see it's not always. You'll see it will not be always easy to associate certain things with one particular thing. Energy, whether you associate with field, whether it's energies, it is stored in the field, stored in the particle. Particle gives rise to field. Field affects the particle. All sorts of complications will come, and all these things will become more relevant when you do that. So maybe in 3-4 classes we'll come to that position.
All right, sir. Thank you.
But I really want you to, for people who are slightly less confident, I really want you to do the variation for the Lagrangian and the Hamiltonian case and see that you get this results, because you might be asked to do it for the later cases when you do electromagnetism, and those variations will be more involved than this. So unless you are confident with this, you won't be able to do those things. And in the class, I won't be able to do variations, because then I will basically, when we'll see later, things become, equations become more complicated, then I'll spend most of the time just deriving the variations that I don't want to do, right? So please do these things. And we'll meet at 4 o'clock on Friday. Okay. And I apologize for all these disturbances, late starting, all these things. I mean, again, on Friday, I will do it from the office, and hopefully these things will not happen.